Hi, I'm Bloem-Reddy. I'm an assistant professor in the Department of Statistics at UBC, and I'm excited to tell you about some of my work to develop models and methods for performing inference on evolving networks when we don't observe their history. And I'd just like to thank the seminar organizers for inviting me and for continuing to hold the seminar series even though we can't have it in person. So firstly, I'd like to acknowledge that I'm recording this talk at UBC Vancouver, which is located on the traditional, ancestral, and unceded territory of the Musqueam people. Okay, so for those of you who are unfamiliar with network data, the simple story is that most of the time, network data is a flattened version of some interaction process. Okay, so we may be capturing social interactions or biological interactions, but the idea here is that we somehow simplify that interaction process into something that can be described using the language of graph theory. Okay, so that language says that a vertex represents a participant in an interaction, and the interaction itself is represented as an edge. Okay, expressing things mathematically using graph theory has been useful, although it's becoming more and more limiting as we want to model interactions in more detail. Okay, so the main ideas behind this talk are distilled in this slide. So for those of you who just want the 5-minute version, you can end the video after this slide. So so there are 3 basic ingredients here, and the first ingredient are a collection of models for evolving networks. And I'll talk about 2 in particular, but in general, models for evolving networks have been very popular in probability and the so-called network science literature. And the main reason for their popularity is that one can formulate simple models based on simple rules to generate networks that exhibit many of the empirical phenomena that we observe in real networks. Okay, these models have been less popular as statistical models for a number of reasons. One of the primary reasons is that we often don't observe a network's history. So rather than observing the entire evolutionary process of a network, we just observe a snapshot at a certain point in time, and that's what we have to work with. So some online networks are changing this to some degree, but for things like biological networks, a snapshot is often the only thing that is possible to even capture. Okay, and if we want to actually model the network as a dynamic process, then we have a missing data problem. The history of the network is missing, and we can't ignore that missingness. Okay, so when we have missing data like this, Bayesian methods often excel. Okay, the missing data become latent variables, and then the goal is to have joint inference over model parameters and the latent variables of the missing history. Okay, by doing that, we try to reconstruct the history of the network and perform inference on the model parameters at the same time. Okay, so these are the basic ideas that I'm going to talk about, and I'll talk about them in the context of 2 particular models and the methods that I've worked on developing for those models. So the simplest model is preferential attachment, and I'll spend most of my time talking about preferential attachment because it's the most that we can actually say things about, and it highlights many of the conceptual problems, the harder conceptual problems, without getting distracted by details of the model. But all this is to say that preferential attachment is quite ubiquitous throughout probability and in various fields. There are lots of different variations and extensions, and so I'll just define the one that I'm working with here. So recall that our model for networks evolves over time, and in particular it grows over time. So for simplicity, we'll let the network evolve in discrete time, where each time step corresponds to inserting one end of an edge into the network. Okay, so each edge has two ends, and each time step will just attach one end of an edge to the network. So here I've shown a network that's evolved for 10 time steps because there are 10 ends of edges. And to illustrate how to proceed, we'll just go ahead and attach some edges. So so the first step is, for simplicity, flip a coin, and that coin, if it comes up heads, tells us that the next end of an edge has to attach to a new vertex. Okay, and so at that point we're done with that end of an edge, and we move on to the next, and we flip our coin again, and now let's say it comes up tails. So now we have to decide where to attach this end of an edge. Okay, so here's where preferential attachment comes in. We just choose an existing vertex with probability proportional to the number of edges it already participates in, the number of connections it has. So the number of connections that a vertex has in the language of graph theory is called the degree of that vertex. So we just attach this end of an edge to any of the existing vertices with probability proportional to their degree. Okay, so those probabilities are shown in the right-hand column of the table here. We have 11 ends of edges that have been attached to vertices, and we just allocate them to each vertex. Okay, so now we sample from this discrete probability distribution, and it came up attached to 3, and so we're done there, and we can proceed. We can attach another edge, and we see this time it didn't bring in a new vertex, it just attached between two existing vertices. Okay, and that's preferential attachment. It's quite simple, and maybe it's not so hard to believe that we can say a lot about it because of its simplicity. Okay, I won't go into it in detail. There's a whole probability literature on things you can say about the preferential attachment model, but probably the most important for our purposes and the most widely known is that that simple model of reinforcing the degrees of already high degree vertices can generate so-called power law degree distributions, or heavy-tailed, more accurately, heavy-tailed degree distributions whose tails are well approximated by a power law. Okay, and the basic idea here is just that degrees are allocated highly unequally within a network, and for example, on Twitter, a celebrity may have a few million or 10 millions of followers, but the median Twitter user has something on the order of 10 or 20 followers. Okay, and that sort of property is not unique to Twitter, but has been observed in lots of different types of networks. Okay, so that's nice as a probabilistic model, and it begs the question of what about preferential attachment as a statistical model? So what if I want to fit preferential attachment model to some data and infer model parameters? Okay, so the starting point, as always, is to write down the likelihood of the model. And here, G sub n just denotes a graph with n ends of edges. So a network in the language of graph theory is called a graph, so oftentimes you'll see capital G. Okay, and then we have model parameters. So in that simple model I described previously, beta is just the probability that my coin comes up heads, so that coin that tells us whether or not to attach a new vertex. Beta is the probability it comes up heads. And alpha is just another parameter that gives the model a little extra flexibility. So when we do that preferential attachment step, we can discount the degree of each vertex by alpha and put all the vertices on a bit more equal footing. Okay, it doesn't change anything fundamental about the model, it just gives us a bit more flexibility. Okay, the key here though is that the likelihood factorizes over the vertices. Okay, so each factor of the likelihood that involves the vertices depends on the model parameters, which vertex, where in the order of vertices the vertex is, the degree of the vertex, and then crucially the arrival time of the vertex. So the arrival time just tells us when in that sequence of ends of edges did that vertex appear in the network. Okay, so in this case, the likelihood has this form that factorizes over the vertices, and it turns out we can optimize this numerically with respect to the model parameters quite easily. And this works well even for really big networks with millions of vertices, tens of millions of edges. If we wanted to fit maximum likelihood to even bigger networks, we could use stochastic optimization. So when we have the arrival times, we can fit preferential attachment models to data quite easily, even really, really big networks. Okay, Bayesian inference is just as easy and just as straightforward to implement, and we've done that in both cases with big networks when we see the arrival time. So just to illustrate, we have a collection of temporal data sets, so data sets with timestamps, and when we have those arrival time, when we have the arrival time observations for the vertices, you can see that even in the case of this Stack Overflow data set with 2.5 million vertices and 63 million edges, we can do maximum likelihood estimation of the model parameters. And I don't have runtimes here, but it's quite fast. Okay, so the main point here is that when we have historical information, even this sort of limited historical information about the arrival time of the vertices, we can easily fit the preferential attachment model to huge data sets. Okay. One downside of this, though, is that preferential attachment is so simple that it's not particularly flexible. There are only, in that case, 2 parameters. Much of that last slide applies to other models for the arrival times that are not just coin flips at each step, but in general, there aren't a lot of parameters, and in particular, there are no vertex-specific parameters. So many practitioners modeling and fitting models to network data like to be able to say something about the properties of specific vertices, and preferential attachment doesn't really let you do that. Actually, it turns out, and this is recent work in the last couple of years that I've participated in, preferential attachment is a Bayesian nonparametric model in disguise, and each vertex does have a hidden parameter that can be interpreted as a relative sociability. I won't dwell on that much more, but this is just to say that preferential attachment does actually have a richer parameterization than it first appears, and is a bit more interesting as a statistical model than we once thought. Okay, so that's all nice, but what if we don't observe the network history? And this is a much harder problem, because our likelihood then, we don't even know which terms in the likelihood correspond to which vertices. Okay, so let's take a closer look at this problem. So we have a model for a growing network, but we don't observe its history. We only observe a snapshot of the network. And since the history is missing and we can't ignore it, we need to reconstruct it. Okay, in general, for any model of network growth, there are a huge number of histories that could potentially have produced the network we observe. Okay, so even for a relatively small network, this number grows combinatorially, and it gets huge really fast. Okay, so taking a Bayesian approach here is useful, and the idea here is we can use Bayes' rule to assign probabilities of to the histories given condition on the network we see at the end. Okay, and so the idea here is we can weight each of the possible histories by its probability under the model. And of course, in practice, there are too many possible histories to do this exhaustively, but we can use Markov chain Monte Carlo to do this approximately. Okay, and it turns out that preferential attachment is well suited to this. And the reason for this is that it's particularly well suited to the type of missingness that the vertices have. So in general, vertex arrival times are left centered, i.e. we know that a vertex joined the network, but we don't know when. Okay, so if you're familiar with survival analysis, then you may be familiar with this type of censoring, and this diagram just illustrates this property. So we observe a network here where this dashed line is, and let's say we have our 6 vertices in our network. So we know all those vertices are in the network. We just don't know when they appeared in the network. So our labels, instead of labeling them in the order in which they arrived, we just have question marks. Okay, so we have left censored vertex arrival times. But it turns out that those hidden variables I mentioned before in preferential attachment, they form a stochastic process that is a Bayesian conjugate prior to left censored data. Okay, so they have this property called left neutrality, and you can show that using them as a prior gives you a posterior distribution in that same family that has left neutrality, and that's what's laying behind that likelihood factorization. Okay, so the likelihood factorization over vertices then that results from left neutrality makes Markov chain Monte Carlo easy to implement and cheap to compute. Okay, so there's a lot that I'm sweeping under the rug here, but the upshot is that it works, and it works quite well, with the caveat that it works quite well up to about 100,000 edges. Okay, so this table just summarizes a simulation study where we generated data from the model we generated networks of different sizes, and then estimated the parameters using Gibbs sampling, and you can see that as the network grows, we get more and more accurate parameter estimation, and our statistical performance in terms of effective sample size doesn't decrease too much. And then the other thing to note is that the computational complexity of the sampler scales linearly with the number of edges. Okay, so we can't really do a whole lot better than that in terms of MCMC sampling, in terms of computational complexity. The limit actually to the current methods is about 100,000 edges, and at that point the statistical properties of the sampler start to degrade. So it just gets a bit too sticky. Okay, so we have some ongoing work trying to improve that, but even sort of the simplest implementation here, which this represents, does pretty well. Okay, so I'm going to spend the last couple of minutes talking about a bit more, a slightly more complicated model, and it's a generalization, can be viewed as a generalization of preferential attachment, and we'll just modify it to try to capture some more of the local dependence that we think is relevant to networks. So again, we're generating the network one edge at a time, and so in step one, we select a starting vertex in the same way as we did with preferential attachment, so proportional to its degree. And then step two, we perform a random walk on the network. So we have our starting vertex, and then a random walk just selects one of the neighboring vertices with equal probability. So it moves here to vertex 2, and then to vertex 1, and so on, and we can make the length of that random walk random as a draw from a Poisson distribution with parameter lambda. And now at the end of the random walk, we just connect the start and the end vertices. Okay, so that's how we insert edges, and of course we can also flip a coin as before to insert new edges. But the basic idea here is that lambda controls the scale of the dependence between edges. So small lambda, heuristically, small lambda means that edges form through local interaction. So if this were modeling a social network, new links are formed primarily through small groups of mutual friends. On the other hand, large lambda doesn't care so much about the local structure of the network, and And as lambda goes to infinity, it turns out that you recover the preferential attachment model, and that's in that case, new links are formed solely based on how many friends someone already has, but not who those friends are. Okay, so the random walk model is more flexible, and it's a higher fidelity model than preferential attachment, and so it should be better for modeling different types of data. However, we lose a lot of the nice probabilistic properties that make inference algorithms for preferential attachment work so well. Okay, so in this case, we have our problem of reconstructing the history again, and it turns out we can still do inference in this case, but it gets a lot harder. So here we have to infer the order of every edge, and sequential Monte Carlo is really the only tool that we can reasonably use in this situation, and even those we had to adapt and extend a fair amount just to get them to apply to this situation. Okay, so sequential Monte Carlo has some known drawbacks. It's computationally expensive, and its performance degrades as the length of the sequence grows. For small to moderately sized networks, actually these methods work surprisingly well, given enough computation time. Okay, so our more detailed model of the interactions, we can still fit the model to data, but that data has to be fairly small. Okay, so just to wrap up, I told you a bit about models for evolving networks and preferential attachment in particular, with a bit about the random walk models. When we don't observe the history of the network, we have a missing data problem, and the missingness can't be ignored. Okay, so to address the missing data problem, we took a Bayesian approach to jointly inferring model parameters in the unobserved histories, and in preferential attachment, we were able to exploit the probabilistic structure of the model to use Gibbs sampling and other MCMC sampling approaches that scale quite well. For the more detailed random walk model, sequential Monte Carlo based methods work for relatively small networks. The benefit there is that for small networks, you may want to have more detailed models, and you can actually fit those models to data. Okay, so there's a lot more to do. I've really only scratched the surface of the work we've done and the problems involved. There's a lot more work to do, and getting the inference methods to scale better is a high priority. And oftentimes in modern applications, scaling Bayesian inference means variational inference. The problem here is that we have a bunch of discrete random variables running around, and so variational inference is not a straightforward not a straightforward thing to do. Okay, something I'm particularly interested in is having better models that are motivated by specific applications. So the models that I talked about today were motivated by fairly general considerations, but I think having models motivated by specific applications is an important way forward. And this is reading not so much between the lines. I'd like to collaborate with some applied researchers in this direction. And then in general, we need better data collection. So ideally, we would be flattening these interaction problems even less, so that we can do more with our models and our inference methods. Thanks for tuning in, and I'm looking forward to the Q&A session.